Good afternoon, I hope you're all well. Today we're going to be looking at motion analysis. Now normally when we do a motion analysis, say of a ball dropping, we would use something like these probes, which are motion detectors. These motion detectors are designed in order to look at distance over time. So the distance a ball moves over the time it takes for it to move, which is very useful. We can also use it to do things like find out the velocity of the ball, the acceleration of the ball, and gravity in this area we are. But that's not the only way. And especially at this time, where we actually do have a virus going around, we need other methods. The next tool that we can look at is doing a video analysis. As the name suggests, what we do is we set up a video camera. We happen to have one right here that I'm talking into. Then we set up our experiment. In this case, I'm going to be doing an extrapolation of the ball drop experiment covered in the key experiments. So for this experiment, we have a few things. We have a ball, most obviously. We have our motion detector set up, and we also have the graphical analysis app. This will be the one that collects the data. So I collect to our motion sensor, and then I'm ready to go. So I'll start with the measurement at 0 and 0 that. And now we're ready to go for this experiment. So 3, 2, 1. So as you can see, we have our data here, and we can do an analysis not just of the position, but also of the velocity of the ball as it bounced. So we have a good amount of data here that we can use. Now, as I said, this is not the only way we can collect the data. I'm now going to take that data and put it into video analysis. So we'll import the video to here. Now that we've imported the video to video analysis, you can see we have an entire run of it. Now we don't need the beginning parts of it, so what I'll do is I'll just run the footage straight to the point where my hand opens. From that point where my hand opens, I can then attach dot points to the ball as it falls down and hits the table. Now I'll set the size and scales. If I click on this option here, I can now determine how big the ball is. This ball, being a standard tennis ball, is 6.5 centimeters diameter. So we can use that data and place it in. So now I have size, I have distance. I now can get a graph with distance and a graph with velocity. So now I have size, I have distance.
Okay, take a break.
I now can get a graph with distance and a graph with velocity. So as you can see, for this,
someone throwing
the
a ball
advantage
and
is
the speed of the ball
flexibility.
in their hand.
From here, I'm able to take a whole host of data
so I can
and
see if they're
analyze it.
bustling quickly,
I
if
could
they're walking
measure
slowly,
someone throwing a ball
or if they're on
and
a
the speed of the
leisurely
ball
stroll.
as it leaves their hand.
I
I
could
can
even
look at
use
people
this
and the speed
to
they're
find out
walking,
G,
so I can see
as
if
I
they're
mentioned
bustling quickly, if they're walking slowly,
G
or if
is
they're on a
worked out
leisurely stroll.
by taking a linear
I could
curve
even
fit
use this
from our
to
velocity
find
graph.
out
So
G,
if we look
as I
over
mentioned
at
earlier.
the data we just took,
Now G is worked
you
out
can see
by
here
taking
that I
a
have my
linear
velocity
curve
graph.
fit
So I go
from our
into my
velocity
options,
graph. So if we look over at
curve
the data
fit,
we just took,
linear, and this m
you
value
can see here that I have my velocity
is
graph. So I go
about
down to my options, my analyze,
about minus
curve fit,
9.8.
linear,
That means
and this n value
gravity, 9.8 meters per
is
second squared in a
about
downwards direction.
is
Now,
about
as I
minus
said,
9.8.
this is about flexibility. But as I said,
So there you have it.
flexibility is
We have
important.
about 9.8
So,
meters
the
per
next
second
bit of
minus
video footage we're
9.8
going to
meters per
take
second.
is
So
from
that's
a
gravity
historical
in a
film.
downwards direction. But as I said, flexibility is important.
This is from
So
one of the moon
the
landings.
next bit of
This
video
is from the
footage we're
Apollo
going to
15
take
moon landing.
is from
For
a
the
historical
experiment
film.
that they ran, they were dropping a feather and a hammer
As you can
to see which one would
this
hit
is
the
from
ground
one of the
first.
moon landings.
Of course, they
This
both
is
hit
from the
ground at
Apollo
same
15
time,
moon landing.
But we can now
For the experiment that
footage
they ran, they were
and
dropping
with this
a
footage,
feather
we can
and a
do the
hammer
same
to see
analysis
which one
we
would
did.
hit the ground first.
looking
Of
through
course, they
this
both hit the ground at the
historical
same
records,
time.
I
But
found
we
the
can now
size of the
take
hammer
this footage,
is,
and with this footage, we can do the
I found the
same
size of the
analysis we
hammer,
did.
and I placed that data
Looking through
into
the
the
historical
video
records, I found the size of the hammer,
I have
and I
to follow the
placed
feather,
that
the size of the
data
hammer.
into the video
I can
analysis.
do my analysis.
I now
I can see
look at the fall
G
of the feather.
on the moon.
Now that I have the fall of the feather, the size of the
To
hammer,
give you an idea of
I can
accuracy,
do my analysis.
this
and I
reading
can
that we
see
have
G on the
almost
moon.
lines up correctly. G on the moon
There I have
is
minus
1.6 meters per second squared.
minus 1.6 meters per second. So gravity on the moon, G on the
Here we
moon,
have a powerful tool
minus
that I hope you all enjoy and
1.6
you all
meters
use,
per
especially
second
in this
squared.
time. Be safe
So
and enjoy science.
here we have a powerful tool that I hope you all enjoy and you all use, especially in this time. Be safe
Try a different ending
and
to that.
enjoy science. Thank you.